If we go look at the make file, there is a test in here. Verify 1 and verify. Let's run verify 1 and verify that we can verify this message. It has a data. It has the hexadecimal of the message, the signature, which should be, 65 bytes long. You'll notice that the last byte is a 0. It's in quadrant 0. And there is the data that it's going to check that you're going to sign. So here is the message. And let's actually try verifying this and see that it works. And it says that for that particular thing that the signature is verified. Now that means it's a valid signature. And when we go and look in the code, there's a verify message. There's some stuff up here at the top about how it does the command line. And then there is this action thing that takes a context from the command line and it pulls out the address, the signature, the message. It uses some sort of a function to get the message and the original message, which is the fourth argument. So 0 through 3. It prints out what that original message is so that we have some output to look at. And then it checks that the message matches the hex of the message. It has the option of some other things, and then it calls this verify signature function. And with an address, a signature, and the message as a string. So whatever that verify signature is looks like a prime candidate for putting in our server and getting it to work inside the server to verify our messages. And fortunately, if we go down a little bit farther, we'll find here is the code for verify signature. So, this may not have the correct data types for what we need back. This has an addresser, a signature, and a message as strings. But I bet you we can take the data types we have and figure out how to match those up or change this function so that it has the right data types for what we need. I think our address is actually already a parsed hex address, but we can use sprintf with a %x to convert that back into a string. And we're going to have to do some testing to see if this particular function does what we need. But you'll notice that here it decodes the hex message, so it's expecting the message in hex. It checks that the address is actually a hex address. Okay. It converts the address to whatever this address type is, a common. Well, we can see what that is, but it's probably some sort of byte hex value. A signature. It decodes the signature. Again, it starts out as hex and it's doing a decode of hex. And then it does this crypto signature sign hash. Whatever sign hash does, we'll have to find that and find out what it does. But basically, it's taking the signature to a public key. I bet pub there is public key of a signature because over here it says recovered public key. And it sees if it got a value back. If it didn't, we know it didn't match. And then it takes the public key and it does this crypto from ECDSA pub recovered public key. So it takes a full public key and it makes it into the 24-byte public key that we use, the partial public key, and it takes the recovered address. And again, it turns public key into address. I bet the first one extracts from an entire key. The public key, the second one, gives us the 24 bytes. And the address, it compares the address we have. That's the parameter up here after we've processed it a little bit with the recovered address. So we verify that not only is the signature a valid signature, that's up here, but then that the address that it is signing for is the correct address. And then it returns some information. Now, if you look at the information it returns, I don't think we need all of that at the end when we're done. It has the recovered address, the public key, and an error. All we're really interested in is, did this fail with an error? Because if it's an error, it's not a valid signature. If it succeeded, then great, we've got a valid signature and we can proceed on. But here's the piece of code. Now, where is this? Somewhere it had sig sign hash. Let's go find that piece of code. I'll give you a clue. I have included sign hash inside the server already, so it is already there. But if we go and grep for that, we'll see that in utils is sign hash. And yes, sign hash. Remember that our message, we needed to take the hash of the message to turn it from a string into a numeric value, and there is a KIAC 256 hash of the message. So basically all that sign hash does is take this hash, but it does something else special for this that isn't just that. See, the message gets added to it, this prefix that includes the length and then the string. And the reason for the prefix is if your values are too small, you end up with a security risk because of tiny values. So it makes it longer by prefixing it with the same thing that Ethereum does. And it also puts in the length. That way, two strings that might have the same hash but have different lengths are guaranteed to have different hashes in this kind of a scheme. So we do some things to the string and then we hash it and return it. So this is already included in the code for the server. But the other routine that we had over here, you need to grab that, modify it, and get it to work inside there to verify signatures. Now, if you go back to the makefile, there are a number of these signature tests out here. Verify one that does a test. There's a second verify. There's a third verify that should verify with a much longer message. Because it looks like a transaction from to amount 55. So it's actually a sample of what you would get if you sent through a message. You could probably cut and paste the data from that and actually do a GET request in the browser and verify that that exact signature would actually work in the browser if you cut and pasted enough stuff. You'd have to cut and paste a lot. It's a long line with a lot of pieces. But it's possible. And one of those things that you can do is play around with the browser being the client instead of the custom client and find out what it takes to actually get it to sign transactions and run them. Now, you'll notice one of the things that we haven't prevented here, if we're allowing that, is the possibility of a replay attack, as in somebody listening in the middle and replaying the exact same signature over and over again and getting the same results to move more money from one account to another. So you should be aware of that. In a real system, like Ethereum, it puts in some checking that every signature that it sees is actually unique and that you can't replay them. We haven't put in that check in our server. Now let's go over and take a look at the server. In the server, okay, in whatever it is, client main example, main.go. You'll notice that there's this function called run server that it runs, that if it's a server, it's going to respond to these different kinds of endpoints by calling different functions. So if it has a list account value, it calls this get resp handle account value. If you go in here, you'll find this function. It has whatever it is it's doing. It says it validates some sort of an account pin, and then it turns around and sets the content type to application JSON. That's to say, the response I'm going to send you back is going to be in this format. It goes out and it gets a parameter called account, checks to see that that's there, and then it calls this routine with account that actually implements the stuff. That routine returns a piece of JSON code, and then it turns around, and what does it do with it? It writes it, and it's done. So most of these functions have some sort of an interface where it takes the request and the endpoint, calls a piece of code, picks out the parameters, processes those into the internal format that you need. In this case, an account, which I think in this case is just a string with the hex values. And then when it gets done, it has a piece of JSON and it just writes it, and that's the response. And that's exactly what you need to build in here for the transaction stuff. So the response that we have somewhere in the CC, which is the CLI package, we can go look at show balance. And it is in here's the function that it calls to actually implement the business logic, which is show balance JSON. And what does it do? It takes the address, which is a string, and it parses it with some function that converts it into the internal format. Then it calls a function that gets the balance for that account. And that returns an integer and prints out the result as a JSON string. So most of these functions, this is how complicated something in a server actually is a lot of stuff having to do with routing, the communication endpoint, processing of the parameters to make certain you have actual real values, and then some business logic that you probably test separately that gives you the results that you are looking for in terms of the business logic.